A very good morning, friends. Today we are going to discuss about micro and nano manufacturing. So in nano micro machining process, the actual material removal can be limited to the surface of workpiece, that is only a few atoms or layers of atoms. At this range, inherent measurement problems and the lack of more detailed experimental data limit the possibility of developing analytical and empirical models, as more assumptions have to be made. On the basis of atomistic contact models, the dynamics of the local material removal process and its impact on the material structure as well as surface generation can be studied. So look at this. This is the concept of molecular dynamics cutting of model setup, that is nanoscale cutting. So the more universal representation further allows you to go beyond the ideal single crystalline structure and also consider the polycrystalline defect structure, pre-machined or otherwise constrained workpiece models and nano smooth surfaces. So various applications specified by boundary conditions may be applied. In recent years, number of applications considering the quantum mechanics for the interaction between the atoms has been steadily increasing. However, here only the more classical atmospheric approach will be presented. This figure 1.1 shows a general description of often applied concept of MD cutting process simulation, that is the orthogonal condition, and it includes the essential elements of molecular dynamics modeling. In addition to the material properties and the interaction between it, constitutes the contact and interface condition, example between the tool tip and workpiece. Look at this. This is the tool tip and this is the workpiece, as well as their environment need to be described. Furthermore, the boundary condition within the model, that is surface versus the bulk material, and the system boundaries to the non-model environments are important. So this is necessary physical elements and principle as well as the area of application in molecular dynamics modelings are explained over here. The mathematical description of the equation of motion in a particular has been included in the listing, since the choice has major influences the numerical complexity and the accuracy of the calculation. So this is the general material representation, and microstructure is defined over here. Look at this. This is the atom surface, this is the boundary, and this is the tool cutting environment. So consider a crystal size. We're considering the crystal size of typical metals, which ranges between few tens to several hundred microns in diameter. A single crystal, or what we called as a single crystalline workpiece structure, represent a reasonable material structure for a nanoscale cutting simulations, as a tool represents reasonable material structure. A tool tip will have a cut over a length of at least 30,000 unit cells before reaching it to the grain boundary area. However, defects in crystal structure like grain boundaries and dislocations, amorphous material or polymers as well as liquids and gases can also be studied using molecular dynamics. The figure in this figure shows a 2D orthogonal cutting setup. The choice of material representation should always be a 3D, even if the width of the model is chosen to be only 1 unit cell wide. The advantages of 2D models lies in the reduced calculation time and somewhat easier visualization of the results. However, these advantages are combined with many disadvantages and great loss of information of meaning of carrying out the atomistic simulations. Where pure 2D models, it is impossible to sufficiently describe the 3D crystalline structure of a metal, and hence no realistic slip system or dislocation motion seems possible, and no realistic information behavior can be expected. So you can see over here, this is the another view of nanoscale cutting. You can see over here, that this is the cutting tool, and material to be cut is over here. So with the increase in the depth of cut, the portion of twin dislocation in chip formation increases, or dislocation slipping. Such a twinned areas can be seen ahead of the tool tip. Look at this. This is the ahead of the tool tip. The lower energy requirement for twinning makes the chip removal process at larger cut depths more efficient, and the cutting forces only increases proportionally. Here, the two subsequent 2D views of microstructural snapshots of the same model as shown in this figure, but a smaller cut depth than before. The analyzing the changes in the microstructure depends upon the understanding of the involved mechanism of material removal for specific cutting conditions. In figure, the different areas of crystal orientation are separated by lines, and slip lines are drawn with identical dislocations. So this is a nanoscale cutting. This is a nanoscale generally cutting. Look at it. This is a generally nanoscale cutting. So in this figure, you can see the areas with different crystal orientations are separated by lines and slip lines drawn for the identification of dislocations. This is the repulsive boundary. This is atomic fluid, or generally called as a water. So the cutting process right before state A was characterized by a growth of the pre-deformation area in the cutting direction. So without any increase in the chip length, this is the process had a pre-deformation areas decreased while the chip grows in the size. The microstructural plot shows the change of the crystal orientation in the chip root area. So look at this. This is the microstructural changes. You can see over here the crack growth in the different directions as tool proceeds. This is the chip formation zone. You can see over here with no peak, and where, look at this, there is a no peak. But in case of further procedure, you can observe the peak which pushes the material to the forward direction. So this is the direction of crack initiation. This is the direction of crack initiation. This is the direction of crack initiation. You can be seen in case of nano cutting. So this is the chip formation in microcutting. You can see over here chip formation zone. This is the, and this is the undeformed zone. Look at this. There is no deformation in this entire area, but due to the metal cutting tool tip, there is a chip formation zone over here. So these are the different types of diamond cutting tools are used. This is the sample one for the nano cutting. So example of nanoscale cuttings are ultra precision lathe. Look at this. This is the ultra precision lathe used in the experiment. This is the experimental setup for the nanoscale ductile mode cutting of silicon wafer with the single crystal diamond tool. Look at this for the micro turning. You can see a very accurate and small cutting is done using a nano micro cutting. So what is the micro turning? In case of micro turning, these are the characteristics, features and applications. You can use the Swiss type machine tools with ultra precision lathes for diamond turning, and miniature desktop machines are used to perform the micro turning operations on part made up of different materials. Here you can see the maximum machining diameter is near about 7 mm, where the maximum machining length is near about 40 mm. So generally it is hard to machine surface such as electroless nickel, glass, ceramics, quartz, etc. without any subsurface damaged. So mirror surface of less than 10 nanometer surface finish can be obtained. It gives the ultra precision diamond turning. Electroless use can be nickel dies or plastic optical parts for LCD TVs which having less than 6 nanometer can be easily turned. These are the micro turning tools and tooling system. Miniaturized tools with clamping. It is having a Swiss type lathe or multi-purpose tooling system used as a tool block. You can see over here. So monolithic carbide tools, boring and grooving, smallest diameter of 0.2 mm to 4 mm maximum can be turned. So micro turning tools, look at this. This is a special tooling system for used for turning, boring and cut off of drilling. This system consists of clamping unit and cutting unit. Machine uptime reduces up to 25 to 40%. So rotating tool head for micro turning operations. Look at this. This is the material feeding device with rotating tool head. This is a raw material. This is the process of rollers which is used for straightening. This is longitudinal feed drive. Look at this. Number 3 is longitudinal feed drive. This is a supportive sleeve. This is a cutting tool. This is the cutting tool, and this is the rotating head. So machine tools for micro turning are generally CNC automatic lathe sliding head having a sliding head mechanism. Generally Swiss type turning centers with having a milling, drilling and boring operations. A single setup with lower cost up to a 4 mm diameter can be easily turned. Having a sliding headstock or dimensions near about 32 mm maximum diameter with bar feeder can be accommodated. So 12,000 rpm with guide brushes and 16,000 rpm with guide brushes can be used over here. So micro turning near about 40 mm length, 4 mm length and 50 micron having a tip size. Look at this micro turning. Micro drilling. What are the characteristics and features for the applications of micro drilling? Having holes near about done on the PCB, having inkjet printer single row of 251 holes with 50 micron diameter used below up to this 0.5 mm and minimum diameter micro drills near about 5 to 50 micron. The advantages of micro drilling is that metal, plastic and composites can be easily drilled and properties do not influence the workpiece. Second is controllability, and disadvantages of micro drillings are inclination of holes, brittle and hard materials, brake micro drills and Dremel drills, etc. You can see there are different types of drill bits having starting ranges from 0.12 mm to 2.8 mm, having a titanium and SS steel. Look at this micro drilling system having a 0.3 mm HSS micro drill. This is the cutting edge, this is the rake face, you can easily observe over here. So micro drills of the smallest obtainable diameter of approximately 6 micron with the D-shaped cross section and a cutting edge radius near about 0.5 micron can be fabricated by wire electro discharge grinding. These are the micro drills. This is a hand wheel with zero adjustable scale, cast iron base and component table of stable aluminum. Both axes are fitted with the adjustable dovetail slides. This is the inner view where air bearings are used or air thrust bearings are used in the micro drill. This is the compressed air supply from this side. This is another machine tools for micro drilling, precision element hard finishing, having air bearing spindle about near about 5 lakh rpm maximum to 18 lakh current, having 1,60,000 having rpm of ball bearing. So you can see over here V-shaped bearing is used. This is the mandrel, this is the micro tool, this is the workpiece on which you have to do the drilling. DC motor is connected. This is electronically balanced ultrasonic transducer and transducer holder can be used over here. Look at this, there are three types of burr are produced in micro turning. Look at this, or micro drilling. Type 1 burr, this is type 2, this is a somewhat smaller size, and this is a type 3 burr. You can see this is a micro lathe, this is a micro entire factory over here. So MEMS part are silicon mirror assembly. Look at this. So micro milling examples are used to create a 3D features in the range of few microns to a few hundred microns. Micro milling is capable of fabricating holes of several tons of micrometers in size for practical applications. These are the micro manufacturing examples. Look at this. A mite measuring 500 micron long sights on the mirror array used for optical data switching. This is a focused ion beam created. This 2 micron wider gear. This gear is having size only a 2 micron. So thank you. If you have any doubt, then let me know.